Hello again. This is Math 2134 coming to you from the College of DuPage. The title of this lecture is Linear Regression Theory and Applications. And as always, I encourage you to be an active learner while you watch this video. Suppose we wish to find a linear equation which is of the form y equals mx plus b. The m, as you recall, is the slope, and the b is the y coordinate of, the y-intercept, and the x and y represent variables. So we want to find this linear equation that provides the best fit to some data. So to determine this equation is to determine what values of m and b should be used. So let's start with an example. So suppose the yearly revenue of a cab rental company are shown this way. So in 2013, this was the revenue. In 2015, this was the revenue. 2017 and 2019. And so what we have then is this data could be listed as X and Y, because what you would be interested in projecting is what would be my revenue in an outer year X. And so you see we get these values. Now notice these are increasing by 2 years each time, and suppose we wanted to know what do we think it's going to be in 2021. So that would be a question that someone could want to know, either if you were running the business or if you were thinking about buying the business. Well, we plot a scatter plot of these data points, and we see that they really don't lie exactly on a line, but we can probably approximate that with a line. So one possible line would be this one. It doesn't go through any of them exactly, but it's pretty close. Another line is this one, and this looks like this might be a better fit because it comes closer to going through the points on average. But when we start thinking about what does it mean to be the best line, we say, well, we could measure the differences between a data point and what is predicted by y equal mx plus b. And so that would be the blue line, what is predicted by y equals mx plus b, and these are the actual data points that we'd have, and we could say, let's examine how wrong are they in terms of what's the difference between the y1 up here and this 5.2, the y2 here and this 8.9, and so on and so forth. But when we look at this, we realize that some of these are negatives and some of these are positives, and some of those mistakes then, or misalignments, would cancel out unless we choose to square each of these differences. Then a plus error will be equivalent to a negative error, and we would have an accumulation of the errors. And that is what the least squares assumption is. The line of best fit, or the least squares line, is a line for which the sum of the squares of the vertical deviations, or y deviations, is a minimum. We're minimizing the error, or the square of the errors. This is called the regression line. Now, note in our example that squaring each y deviation gives us a series of non-negative terms that we can add. So for example, if we want to know what is the error associated with the data that we just talked about, we would find it will be y1 minus 5.2 whole squared, y2 minus 8.9 whole squared, plus y3 minus 11.7 whole squared, plus y4 minus 16.8 whole squared. And since these points on the line must be solutions to y equal mx plus b, it follows that y1 happens when you put 1 in there, so we get mx plus b. We get y2 is equal to this, y3 is equal to this, and y4 is equal to this. Now, so y1 and then it's going to be mx plus b, y2 is going to be 2m plus b, and so on and so forth. So we're going to substitute that into this equation, and so we'll get this. Now notice that this now is a function of two variables, because we still don't know what m and b are. That's the whole point, is we're trying to figure out what m and b are that will minimize this. And you notice this is very similar to a problem that we've already studied. We have two variables and we want to find the minimum. So we substitute those in. We get this expression squared, and so on and so forth. Now, to find the regression line for the given data, we must find the values of m and b that minimize this. And recall, we learned that we have to do the d-test. So the first thing we do is find the partial derivatives. And when we take the partial derivatives, they'll be kind of simple, because each of these, we're taking the derivative with respect to b. So this is going to be 2 times this business. Actually, down here, it'll be 2 times this business, plus 2 times this business, plus 2 times this business, plus 2 times this business. And so that's what we will get. And we can collect like terms, and we get that this is going to be 20m plus 8b minus 85.2 when we simplify it. Now similarly, we can do the same thing with respect to the m. So the partial with respect to m, we're looking at this expression, so it's going to be 2 times that business plus 2 times this business, and so on and so forth. And so we're going to go through and do that. And then what we're going to do is we have to realize, oh, but since we're taking the partial with respect to m, I have to use the chain rule. So here it is just a 1, but here when I take this, this is going to be 2 times this business, but there's the chain rule too. It's going to be 2 times this business, but there's the 3 by the chain rule. 2 times this business, but then there's the 4. So I simplify all of that, and I get this equation that involves m and b. So now I have this equation and this equation must both be equal to 0 to be a critical number. So I can take those derivatives equal to 0 and solve the resulting equation. So I can take this equation and this equation, they're simplified a little bit more here, and I can solve them. Now if I take the top equation and solve for b, I get this, and then I can substitute b into the second equation, and I can solve for m. You should verify these calculations, but m ends up being 3.76, and then you can find b by reversing the substitution. I'll take the 3.76, substitute it in here, and get b is 1.25. Now you can, and I encourage you to do this, to complete the d-test to verify that this is in fact the minimum value. But you see, we really don't have to compute what the minimum value of this is, because what we're really trying to do is find out what was m and what was b. So you see, m is going to be 3.76 and b is going to be 1.25. That means the best line that we can put through this data is y is equal to 3.76x plus 1.25. And if we wanted to predict 1 year out, we would take this equation and we would take 5 as our data point. And that would give us a predicted value up here. So the yearly revenue in 2021 is predicted to be about 20.05 million. Now, this method is demonstrated for only 4 data points to get it, and most researchers would want more than 4 data points to get a good regression line. And in fact, I'm going to give you a problem where there are more than these and you have to do it. A further point is making predictions too far in the future in any mathematical model may not be valid. So we have to be skeptical about future predictions. Let's talk about doing this in general and see what equations we might end up solving. So what we're going to do is trace our paths. So to find a method for computing the regression line, suppose it has a representation, again, it is y equals f of x equal mx plus b, and we have to figure out m and b. But now, and I'm taking 5 things here just to get a handle on that, so if we had 5 data points, we'd be looking at the square error, it's going to be this expression. And substituting this in, and notice that now I'm not taking the specific values, I'm just saying what happens with the x values. So here we have x1, y1, x2, y2, x3, y3, x4, y4, and x5, y5 as my data points. So we have this is my square error as before. And if we use the chain rule and we take the derivatives using the chain rule, we'll have the partial with respect to m is this. Now notice this time through, when we take the partial with respect to m in the chain rule, we're going to get x2, x3, x4, and x5 popping out, not the numbers necessarily that we had before. And we reorganize this, and what we end up with is that this, we're going to set this equal to 0. So we have 2 times, we collect these are the square terms, times m, plus this is just the sum of the x terms times b, and we subtract off the products of the x's and y's. And we're going to set that equal to 0. Similarly, we're going to take the partial with respect to b. Now this time the chain rule doesn't become apparent. And we're going to set this equal to 0, and we'll have this. So that means we have 2 equations and 2 unknowns. The first one is going to be the sum of the squares of the x values times m plus the sum of the x values times b is equal to, and I put these products on the other side. That's what we get from one of these equations. The other one, similarly, is going to be the summation of the x values times n plus, and then this is going to be 5. Now 5 really is the number of data points that we had, so this would be n in general, is equal to the summation of the y's. And so if we solve these simultaneously for m and b, which we did before, that tells us what m and b are. Now before looking at another example of this, where we're just going to use the formula then, here is the theorem. So suppose we have n data points, x1, y1, x2, y2, x3, y3, dot, 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 as many as we want, x4, y4, and then all the way up to xn, yn. Then the least squares regression line for the data, given by the equation y equals f of x equal mx plus 4, mx plus b, where the constants m and b satisfy these equations. So we take the summation of the squares times m plus the summation of the x's times the b is equal to these products. And the other equation is the summation of the x's times m plus n, the number of data points we have, times b is equal to the summation of the y's. These two equations are called the normal equations, and these are the equations that we will have to solve to find m and b in general. So let's take an example where we have 5 data points. Then what we have here then are all these matching what are the x's and y's. Now, one of the normal equations is we add up the sum of the squares of the x's times m plus, this is the summation of the x's times b is equal to the summation of the products. You see you have 1, 6, 12, 12, and 30 as those products. So this is one of my equations, and I simplify it and I get this. 55m plus 15b equals 61. Now the other equation becomes the summation of the x's times m plus how many data points we had? We had 5, is equal to, and again this is going to be the summation of the y's. And simplify, I get this. So I have this equation and this equation, 2 equations in, 2 unknowns. You know how to solve it. We can solve it by substitution. We can solve for b in this equation and substitute it into the other one. Solve for m. So m is 1, and if I put 1 in there for that, I get b is 0.4. So the equation is y equals x plus 0.4, and here's the scatter diagram and the regression line plotted. And you see that's the best that we can do because we executed this process. Now, we can do a little bit bigger example. Here we have 1, 2, 3, 4, 5, 6 data points. We're going to do this in a little bit more power way. So you see what I'm going to do is I'm going to summarize this by listing the x this way, the y this way, and then I'm going to square each of the x's because I need that, each of those values, and then I'm going to take x times y and I will add them up. So these are going to be the sums of each totals. So you see now I know that the equations are going to be 6, and there were 6 data points, times b plus 120, that was the summation of the x's, m, is equal to 540. And 120b, that's going to be the summation of the x's again, plus, and this is going to be the summation of the x squareds, times m is equal to 11,530, which is this sum. So you see that's where all these numbers come from. So these are the normal equations that we need to solve. Again, we solve by substitution. And we'll get that m is, and here we're rounding off a little bit, m is approximately 2.97. And b is going to be approximately equal to, this is approximately because the other number was approximate, 30.6. So that means this is the line of best fit here. 2.97 x plus 30.6. And if we wanted to estimate the profit at corresponding to an annual budget of 20,000, we will put 20,000 in there, and we will get 90,000 as that data point. Now, this process could be expanded for other forms of regression that we often consider in this text. So in this following example, we show how an exponential regression model can be developed from a set of data. So here we have a table that gives us the yearly revenue, and this is the number of years since 2016. This is the revenue in thousands of dollars. And we want to find an exponential model that best fits this data. And if you plot this, you say, oh, maybe this is going up in exponential growth rather than a line. So we're going to say, I want to find a function of the form y equals a times b to the x. And the unknowns here are going to be a and b. X and y are going to be variables, and there's our data points for x and y. Now we're going to use linear techniques as we've had. So what we're going to do is we're going to change this into a linear equation by finding the natural logarithms of both sides. So we'll say the ln of y is equal to the ln of a times b to the x. But that's a product of a times b to the x, so that's the ln of a plus the ln of b to the x. And then we're going to use the property here that the ln of b to the x is x times ln of b. So you see, this is starting to look like a line, because here's going to be some numbers, here's going to be some numbers, and here's going to be x plus x times ln b. So you see, if we relabel y as y tilde and b as ln of b, this is ln of y is y tilde and ln of b is b tilde, then we have y tilde is equal to b tilde plus this, and this is a tilde, which is going to be ln of a. And we take those numbers. Now here we have x, y, but now we're also going to be looking at y tilde. So y tilde is going to be the natural logarithm of these values. So now, if we start plotting these, we say, oh, this does have more of a linear relationship than the original scatter plot seemed to. So we can use the method outlined previously to do a linear regression on these points. And when we do that, we can find that b tilde and a tilde, the unknowns in our regression, were 0.579, and this was approximately 4.968. But then we know that the ln of b equals b tilde, so b is equal to e to that b tilde, so this is e to the 0.579, and similarly a is equal to e of a tilde, and so this is e to the 4.968 equal this, so we can solve this model, and we will have that this is going to be 143.74. So you see the regression model is then y is equal to a b to the x is equal to this expression. And if we use this model to estimate the revenue, when x is 6, we would get this. So you see, we can use linear regression as a way to do exponential regression. In summary, regression is a technique for determining a continuous function, a continuous line, that best fits a set of data points. According to the least squares assumption, the line of best fit is the one for which the sum of the squares of the y deviations is a minimum. We did use calculus very fundamentally to come up with equations for m and b, the line of best fit. And for exponential regressions, calculus is used to find values of a and b that determine the exponential regression curve y is equal to a times b to the x, which best fits the data. Now, looking ahead, in statistics we address even more complicated considerations. But as you have seen, we can do this for any set of data, with the fit of the line being the best we can do, according to the least squares assumption. But is the fit good enough? I should have put another quote at the end of that to use. This important consideration is addressed in statistics courses, and I would recommend you consider taking such a course as part of your studies as you go along. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.